All right, you guys. This is the third installment of similarity, and these problems look worse than they are. There's a lot of writing to them, but they're not as hard as they seem. What they want you to do is understand which sides are proportional to which sides. Okay, so you have two triangles here, and you can kind of tell, obviously, if you're just looking at it, eyeballing it, you can tell which ones they are kind of estimating are the same. Okay. The way you would always know is that small is to small, middle is to middle, and large is to large. Like you can identify the smallest, medium, and large size, right? And you can compare those in each triangle, and that's what you would be comparing. All right. And it says there are three proportions below. The ratios in each proportion compare the length of one of the sides of ABC, this one, that's important to pay attention to which one they're talking, to the length of the corresponding of X, Y, Z. I'm missing the Y here. Complete the proportions. Okay, so they're just trying to get you to compare the sides. AB is to AB rather, this way. AB is to XY as AC is to XZ. Okay, so the XZ would go here. It's important that you name them in the same order. Okay, BC is comparable to YZ. All right, and then you're supposed to find the actual ratio. So AB is 6 over, okay, XY, which is 8. And you can reduce it. You always want to reduce it. So that reduces to 3/4, right? So that reduces it to 3/4. Okay, and then AC is 15 divided by 20. And then those are both divisible by 5, so they reduce to 3/4. So look, you guys, each ratio is the same. Not proportion, each ratio is the same. That's how you can tell two triangles are proportional. If two triangles are proportional, then every one of their sides would be proportional, okay, by the same scale factor, the same ratio. Okay, so come here, choose this correct statement. It says each pair of side lengths compared is not the same ratio. Well, it is, so move on. Each pair of side lengths is not, nope. Each pair of side lengths is in the same ratio. This is coincidence. We would not usually expect this from similar triangles that are not the same size. No, that's stupid. Okay, so it must be this one. Okay, each pair of sides, same ratio. This is because the side lengths in each pair are lengths of corresponding size and the triangles are similar. If you want to use wording for your notes, there's a good piece of wording for you, okay? That corresponding sides are proportional. All right, next. So basically, you're just trying to figure out the proportion by putting it as a fraction. Okay, I'm going to go ahead and make this larger. Okay, we'll move it over. Come on, honey, let's go over here. Okay, so we've got triangle ABC and triangle DEF. Okay, so again, small is to small, medium is to medium, and large is to large. I'm just doing that for just to point it out, okay? Complete the three pairs, AB to AC. Okay, now we're not comparing triangle to triangle, we're comparing sides on the same triangle. So check this out, this is actually quite fun. AB is 15 and AC is 12. Okay, if you reduce that, that becomes, they're both divisible by 3, 5/4, right? Now look at AB, AB to BC, AB to BC, which is 6, okay? And that reduces to 5/2. And then AC to BC is 2. 12 divided by 6 is 2. So now we have kind of the ratios of side to side. Okay, so this is large to small. This is AB, large to really small. This is large to medium, large to small. Okay, and this is medium to small. All right, so when you compare, you want to compare the same sides, same sides. So if they did AB over AC for this one, we want to do DE to DF. So it's going to be DE. We want to do the comparative sides, the corresponding side. Okay, and then look, it's 5/4. Look, they have the same ratio. And then this time we did AB. Again, that's DE, okay, over EF, and that's 5/2. Look, 5/2, 5/2. It's the same. And then DF, which is 16 over 8, is 2, and that's going to be FE. Okay, so basically you're just naming corresponding sides, okay? And then what's cool about it is you can set up these ratios, okay? And it's cool. Even if you're on the same triangle, if you did, say, triangle A, and assuming these are similar, if they are similar to triangle B, you can compare like large side to small, and that would actually be the same for both triangles. That's what we're proving here. It's pretty cool. Large side, in case you didn't know what I was talking about, large side to the small side. You can compare any two sides and you're going to get, if they are similar, you're going to get the same ratio. It's pretty cool. In each pair of proportions, the lengths of the sides ABC are not in the same ratio. Okay, that's not true. In each pair of proportions, the lengths of the sides ABC are not in the same, no, that's not true either. In each pair of proportions, the lengths are in the same ratio, and this is because we compared the sides of DEF that correspond. You're going to be looking a lot for this word right here, correspond. Okay, we want to make sure we're always comparing corresponding. Okay, now I don't know what's underneath this fourth answer. In each pair of proportions, the lengths are in the same ratio. This is a coincidence. Okay. I wonder if there's ever a coincidence. I just think that's a funny answer. But basically, this is going to be true all the time for similar triangles, and that's what we're looking at. Okay, so again, I'm going to make it a little bigger. It says finding angle measures. Okay, come on. Finding angle measures and side ratios to determine if two triangles are similar. So the question is, are these triangles similar? And this is something you're asked a lot to do in when you're dealing with similar triangles. Like, are they? There's a big question mark. Okay. So what we're going to do is, well, they're going to guide us through it because they're going to give us information here. Okay. Again, I often think it's really helpful to just take, yeah, that's ugly. Sorry. That is kind of oogly. Okay, let's try doing a little bit better job. Okay, I'm going to take out ABC so I can write on it. So if you guys are doing this at home, it's helpful. And it's helpful to try to figure out which sides correspond. Okay, so if you look, and these aren't exactly easy. Oh, they told us. Never mind, they told us. They said, wait, consider, oh no, they did not. They didn't tell us. So you have to try to think, okay, which one is the corner? We can tell that A corresponds to D, correct? If we're comparing them. Can you see that E and B are smaller angles and F and C are like they are obtuse? So we would be comparing E and B and then C and F, okay? All right, so now we're looking in triangle ABC, the measure of angle A is 22 and B is 50. Okay, and in DEF, the measure of angle D is 22 and E is 50. So yes, we were comparing B and E and that was correct. Use this information to find the following angle measures. What is angle C? Okay, that's where the 180 thing comes into play. So look, you got 50 plus 22 is 72, and we subtract that from 180, and we will get 108. Okay, so that means C is 108, which means F is also 108 because it has the same two measures. Use the ruler to find the side lengths for each triangle. Assume all lengths are whole numbers. So you just got to grab the ruler and you got to measure these side lengths. Okay. I can't do that. I can estimate it though. Can you guys see? I could call this 1. If I called this 1, by the way, I'm not sure that this is it, but can you see that this would be 2? Because it would be 2 of those little guys. I'm just estimating it, but I can tell. I can tell. And then this one, let's see what this would be. This looks like it would be 2, because look, 1, 2. And then if I measure this, it's going to be 4, no doubt. There you go, 4. And then this one looks like it's going to be 3. Ooh, wow. This doesn't look like it's 3. It looks like it's 2.5 or something. Yeah, I'd call this 2.5. And this would probably be then 5. Okay, in other words, each one of these is doubled. 1 to 2, 2 to 4, 2.5 to 5. And then what you would do is you'd get the angles by measuring, get the side lengths, okay? And you'd put them all in here. And then you're going to find the ratios, AB to DE, okay? AB is 5, DE 2.5, and that would be 2. BC 2 to EF 1, that would be 2. CA would be 4 over 2, FD 2 equals 2. In other words, this is called the scale factor. 2 is the scale factor. This is twice as big as that. Every side is twice as big. Okay, and then we need to answer the last question. 3 pairs of statements are shown below. For each pair, select the true statement. Okay, so just pay attention to the details in the wording. The angles in ABC have the same measure as the angles in DEF. True, right? True. The ratios of corresponding side lengths are all equal to each other. Indeed, they are. The triangles are similar. The triangles are not similar. Yes, they are similar. Okay, we knew they were similar, by the way, simply by this. That proves they're similar. If they have the same angles, they are similar. You could also prove it without the angles if we had the ratios of the sides. That would prove it's similar. You don't need both conditions. You could have either or. All right, so here we are again. Okay, so it's the same. Actually, you know what? I am going to leave this because this is going to be one that's better that you do by yourself. But just know that you want to take a look and make sure you can kind of tip these triangles in the same direction. So A is comparing to D, see, because this is the base and this is the base. Yeah. Okay. And you are going to be measuring these with your ruler and getting these ratios and then answering the questions. Yeah. Okay. Similar polygons. It says, now this is important. Sometimes you have to prove they're similar or check and see if they are. And sometimes they tell you that they're similar. If they tell you that they're similar, then what you can do is set up a proportion to solve. Okay. Proportions are your friends. Proportions are your friends when you have similar triangles. So the reason why we did so much work with proportions is because we're going to start using it now. So look, they want X. Okay. So all you have to do is set up a proportion. And just remember, you have to have samey, same. Okay. Samey, same. Whatever you're talking about here and here has to be the same here and here. So watch. If I want to find X, the corresponding side would be here, 2, correct? So I could go X over 2. Now, what did I put? I put the small side over the large side. You see? I put the small one over the large one. This is a larger shape than this one, quadrilateral. Okay, equals. Then you set up a proportion. You can pick any side, you guys. You can pick 2 to 4. You can pick 2.5 to 5. You can pick 1.5 to 3. It doesn't matter. I'm going to pick 2 to 4 because they're integers. 2 over 4. Rule of thumb, guys. Rule. I always say, stay away from decimals, don't do decimals. Well, guess what? You can use decimals if they give you decimals, okay? So now you have your proportion, and then look what I did. I put small over large. See, samey, same over samey, same. Then you cross multiply, okay? And you're going to get 4x equals 4. And you can tell that x is just going to be 1. And that's what they wanted. Find the length x of QR. It equals 1. Now, I'll be honest with you. If you guys were in a test like the SAT and they were looking at it, you could absolutely just do this in your head. You'd be like, wait, 2 to 4, 4 to 2. You could go backwards. 4 divided by 2 is 2. 2, that would be 1. Like you could actually see it and just manipulate it. I just need to show you the math, the official way to do it, because sometimes it won't be so easy. Like that one, I know you guys could do that one in your head. Okay, you probably can do this. Maybe you can't do this one in your head because look, it's got some weird funky fractions here. So all you need to do is identify the similar sides first, and it's pretty obvious here, okay? So it says the quadrilaterals are similar, and they tell you the letters, by the way. A, B, C, D, J, K, L, M. They're giving you the same ones. Find the side length of KL. So we're going to go x over 7, okay, corresponding sides, equals, pick any other two sides, okay? I'm going to pick 7.2 over 4. I picked that because it was I don't know why, it just seemed easy to grab. So I picked this one over this one. So notice I did large over small, okay? And then you can cross multiply and solve. 7 times 7.2 is 14,150. Move the decimal in, 50.4. Divide by 4. 50.4 divided by 4. I don't recommend that you do this all by hand, y'all, because why would you? You can just use a calculator. Goes in there once, down, goes in there twice, bring it down, 6. Okay, 12.6. Okay, I'm going to erase this. Now, don't get all stressed out about which side to pick, because I want to show you something. As long as you put samey, same, just remember the rule of samey, same. Let's say you decided, oh, wait, I want to do this side instead. I'm going to do these two sides. I could have done x over 7.2. How did that relate? This is all large. Okay, this is large, that side over this side. And then I could have put that equal to 7 over 4. 7 over 4. I could have put the same two sides. Now check it out. When I cross multiply, I get the same thing. 50.4, right? If I picked x, and I could have put x over 3.6 and 7 over 2, and if I cross multiplied, I would still get the same answer. It doesn't matter as long as you put the samey same over the samey same. That's the main thing. Identify corresponding parts. Okay, now this one. What they did was they cut a line here. Okay, if you turned it sideways like this, we would call it dropping a perpendicular. Okay, basically you just cut it here. Okay, find the length x. Now, I can tell you right away that if you have this situation, these two triangles are similar. Why? Because they share two angles. Look, they are both 90 degrees, and they both have that same angle. You see, they both have that angle. You could actually separate these triangles like this. I could separate the little one here, and this would be x, and this would be 7. And then I could draw the bigger one here. This might help some of you that have a hard time like with the visualizing what's happened. Okay, and this is importante, people. Let me do this better. Okay, well, that wasn't much better. I tried. Okay, well, look, this is 8 on the big one. But look, what's the whole side? It's not 7. It's 7 plus 7. See, it's the whole side. So it's 14. So sometimes it's really helpful to take these two triangles out so you can see the relationship. draw them better than I did. I did not do a great job drawing them. And then to find x, just again, a proportion. X over 7, I put this side over that side. So I would put this side over that side, equals 8 over 14. Or you could do x over 8, small side, small triangle, large triangle, equals 7 over 14. It doesn't matter. You could even flip it. You could do large over small is equal to large over small is equal to large over small. Get it? It's okay. It's all okay, because no matter what, when you cross multiply, you're going to get 14x equals 56. See? 14x, 56, 14x, 56. It doesn't matter as long as you get samey same over samey same. Okay? 14, 14. X is equal to probably 6, you guys, because 4 times, no, wait. 4 times 4. No, 4, oh yeah, probably 4, because that's 16. Yep. X is equal to 4. All right, I just really want you to not worry about the lengths as much as just identifying the corresponding parts and making sure you set up your proportion correctly. So again, here you go. Let's break up this triangle into 2. Here's the little guy, 6 and x. And then get the big guy. Okay, and this is going to be 3.5. And this is going to be what? We want the whole side. So we have to walk 6 here, and then we have to walk another 4.5 here. So the whole side is 10.5. Set up your proportion. Doesn't matter, however you want. I honestly probably do same sides more than I do opposites, but I'm going to do this just because why not? So I did small over large equals small over large. Biggest mistake kids do is they'll do like small over large equals large over small. Don't do that. Okay. You can even write the words if it helps. Small, large. Okay. And then you cross multiply and you solve. 10.5x equals 3.5 times 6. Should be 21, but I'm not. No, it's not. It can't be 21 because 6 times 5 is 30. Ooh. Okay. Well, 3.5 plus 3.5 is 7. Oh, 7 and 7 is 14, and 7 is 21.5, probably. Okay, let's try that. 3.5 times 6, 30. I don't know why I kept getting a 0.5. Well, because I was multiplying by 3. I don't know why I was doing that. Okay, here you go. It was 21. It was 21, you guys. I thought I was wrong. Okay, 21. Okay, and this is 10.5. So we're going to divide both sides by 10.5. And look, 10.5 plus 10.5 is 21, you guys. So it's 2. You could do it in a calculator, but that's how you would do it. So now we got x is equal to 2. Again, you're just setting up proportions and solving them. Okay? Try the next one. All right, these are my absolute favorite ones. I don't know if we're going to be able to do them at school. These are fun to do in person. What it is it's how we measured, it's how the Greeks measured the distance to the moon, like from Earth, way back when. We're talking 2,000 years ago, right? They did it with shadows, and they could tell how tall a mountain is using this shadows and triangles. Is super powerful and very cool if you think about it, that they literally manipulated or trigonometry, if you will, right triangle work in order to find how far something so far as the moon was, right? Crazy. Okay, so here's what's going to happen. You're going to have something that's vertical. It's a pole. Okay, it's a tree. It's a house. It's you. It's a cane. It's an umbrella. It's something that is vertical. Okay, and it's going to always be perpendicular with the ground. Okay, so there's a ground here. Okay, so the idea is that you have this pole stuck in the ground. It's at a right angle, perpendicular. So what do I have? I'm going to have a right angle triangle in a second. Okay, and then you got to imagine that there's the sun. Okay, and the sun is here. Okay, and if any of you guys are artists, you'll understand this immediately. What happens is the sun shines, right? And it's able to shine until it hits here and it can't go through, right? So this building, or this pole rather, is going to cast a shadow at the angle of the sun. Okay, so you can see as the sun would go higher and higher, that's why you have no shadow at 12 o'clock, because the sun's rays are coming directly down. Okay, but it's a pole that is 2.5 meters. See, casts a shadow that is 1.44. This is how you draw it. Draw the picture. Do not try to do these problems in your head. That's ridiculous. Don't do it. Okay, this is the shadow on the ground. Okay, shadow. All right, at the same time, a nearby building casts a shadow. Now we're at a building. So here's the pole. It's 2.5 meters. A meter is 3 feet. So if you're thinking about it, that's like, I don't know, 8 feet or something like that. And now we're at a building. So in my picture, I can't really have a great picture of a building. You know what I mean? Unless, of course, the building, hey, maybe the building's a shed. Okay. So it casts a shadow at the same time. So remember, the sun is still getting, the rays are still coming at the same angle. So look, it's going to cast a shadow too. Okay. And that's going to be a perpendicular. So here's my building. Here's my windows. Yeah, and this is built like this weird, like it's some kind of weird newfangled building that has circle windows because I'm tired of drawing them. Okay. All right. Do you see the two triangles? This is a right triangle and this is a right triangle. And what's cool about this is you have similar triangles because the sun's rays are coming down at the same angle. At the same angle. It's the same time of day. It's the same angle. I can't draw the nice picture of this. I'm sorry. I tried. Okay. So basically, we have that the building, oh no, the shadow is 35.75 meters long. So I have two situations. I have this pole and it's casting a shadow, and then I have a building and it's casting a shadow. Okay. How tall is the building? Round your answer to the nearest meter. That's a whole number. So look, how tall is the building? They are looking for the height of the triangle, okay? Height of the building. So you have your triangle. So all you have to do, these are two similar triangles. So all you have to do is put samey same. H over 22.5 rather, that's the height of the building. Building over pole, okay, is equal to building 35.75 over pole 1.44. And then you just simply cross multiply and you would get your answer. 1.44H is equal to 2.5. Hey Siri, what is 2.5 times 35.75?
2.5 times 35.75 is 89.375.
That's how you do it when you're lazy. What is 89.375? Hey Siri, what is 89.375 divided by 1.44? Hey Siri, what is 89.375 divided by 1.44?
89.75 divided by 1.44 is about 62.326.
Okay, she's sort of that. She didn't know how. Okay. Hey Siri, 89.375 divided by 1.44.
89.375 divided by 1.44 is about 62.0659.
Okay, it says to the nearest meter. And there you go. So this is less, this is 0, so we don't round up. Okay, if this were 5 or greater, we would round up. So H is approximately equal to 62 meters. That's it. It's basically creating a situation where you have two similar triangles, and it's so much fun to realize. My son's geometry teacher, I just can't do it because I don't have the confidence that all of my kids have transportation. But my son's geometry teacher had them try to measure the height of the sandias by waking up before dawn, right? And then going and waiting with a person, a person that could help, hold a pole. They would hold a pole, measure. As soon as the sun came up, they'd run to try to measure the shadow and then measure the pole shadow. It's pretty crazy. But I remember doing it. I'll tell you what, because he got me up so early that day. All right, it says a pole is 2.5 meters, casts a shadow. Let's put the sun over here this time. Okay, so I'll do it this way. Boom. My shadow's in this direction now. Okay, still a right angle. This is still a pole. 2.5 meters, 1.67 meters long. Now, you don't need to put the meters there. It's good to check and make sure that they give you the same units. When you do your math, don't put the meters in, okay? At the same time, here we're back to a building, okay? So let's pretend the building is like a big fat building here, okay? And then at the edge of the building is the shadow. And this shadow is going to be 37.75 meters. And then it's asking you, how tall is the building? Sometimes they ask you for the hypotenuse, guys, and you have to use the Pythagorean theorem. Okay, I haven't found that right now. It seems like they're giving you these basic problems, but make no mistake. Sometimes they're like, a pole has a rope. So instead of this being some makeup line, it's actually like a rope. And they're like, how long is the rope? And then you have to use the Pythagorean theorem once you get it, or for this one. Anyway, set up your proportion. H, I'm going to put it side over side. So I'm going to go big building here, building, and here I'm going to put pole on this side. So I'm going to put H over 37.75. So I'm doing it, I'm purposely mixing it up so you guys know what you're doing and you're not just following one example to the other without thinking. Is that 1.67? Because that's ugly. Yeah, it is 1.67. So you get 1.67 equals 2.5 times 37. Sorry, I'm going to use Siri again because I just don't want to plug them in. Hey Siri, what's 2.5 times 37.75?
2.5 times 37.75 is 94.375.
Ooh, did I forget my variable? Yes, I did. My variable is supposed to be right there. Divide by 1.67. Divide by 1.67. And now I'll just do that. Divide by 1.67. It's 56.5. Ooh, 56.5. That means it's 5119, blah, blah, blah. Who cares? This is 5. That means this jumps up to 57. In other words, it's closer to 57 than it is to 56 meters. Okay? And that's your height. And that's the end of this particular video.